Good afternoon, everyone. I'm Yaoqi from National University of Singapore. Today, I'm going to present our recent work on inference attacks and mitigations in peer-assisted CDNs. This is a joint work together with Guangdong, Purdy, and Zhengkai. First, let's talk about the web content delivery. Recently, there are many popular websites like Facebook and Google. These websites receive millions of hits per day across the world. They want a faster way to deliver web content. There are several options for them to deliver web content to users. First, they can set up their own servers and host these web contents on their servers to the users. Or they can pay for content delivery networks, aka CDNs. And these CDN services will place their web contents into different countries and major cities to get their content closer to the users. Recently, there is another new service called peer-assisted CDNs, which can also help these websites to deliver contents. The basic idea of such services is to involve web clients to provide content to other users. Basically, convert the traditional server and client model to client-client model. These new services include Akamai and Swarmify. Basically, they can bring a lot of benefits to users and website operators. For example, NetSession can offload over 70% of traffic from the website server to the peers. And Swarmify can reduce over 60% of network latency for the users. However, they also introduce some new security problems. For example, since all the clients can deliver contents to other clients, these clients actually can infer the neighbor's contents in this way. As an advanced conclusion, we make the following contributions. First, we introduce inference attacks on real-world services, and we propose our solution called Anonymous Peer-Assisted CDNs, aka APAC, to involve browsers as peers to deliver web contents and preserve a high level of anonymity and achieve desired performance. And at last, our solution is compatible with mainstream browsers. So what's inference attacks in peer-assisted CDNs? The goal of inference attacks is to infer what content a victim user has requested or delivered, that is, browsing history. Audience may question about what's the damage or implication of such attacks. From the previous studies and research, we found that revealing a user's browsing history can significantly leak the user's privacy. For example, a user's digital identity can be revealed from the visited social network websites, and a user's geolocation or political orientation can also be leaked via the browsing history. We classify inference attacks into two categories, that is, passive and active attacks. For the passive attacks, the adversary pre-stores all the content potentially interesting to the victim, and when the victim sends a request to the server will instruct the adversary peer to deliver the content to the victim. This way, the adversary can learn what the victim has requested. And for the second class of attacks is the active attacks. In this attack, the victim may first send a request to a server and fetches some resources and store in the browsers. Then the adversary sends request and traverses all the content potentially served by the victim. And then the server instructs the adversary directly fetch these resources from the victim. This way, the adversary can learn what content the victim has served. We launch our inference attacks on three real-world services, that is, Swarmify, BTV, and PPSP. These services basically use users to deliver static resources like images or stream live videos to other users. Take Swarmify as an example. We deploy a website using Swarmify with 10 images and 2 videos. and place a victim peer to request and store resources from these websites, and place another adversary in the same network of the victim, and it also requests and serves resources from the websites. From our experiments, we found that basically for all the three services, there is no defense against inference attacks. That is, the adversary can observe all resources from all to the victim. And one of the three services is even open for content pollution attacks. Now we can see inference attacks are a real threat to peer-assisted CDNs. So how can we mitigate such attacks? We propose our system called anonymous peer-assisted CDNs. The goal, we consider a peer who initiates the request as the initiator and a peer who responds to the request as the responder. We consider an honest but curious adversary which follows protocols, and CPU attacks, denial of services attacks are out of scope. We have three goals for our system. The one is the anonymity. Our system should conceal a user's identity to unlink her ID with her online trace. And also, performance and compatibility are also within our considerations. One intuitive idea to achieve these goals is to utilize ARNI routing techniques. However, we found that directly applying ARNI routing techniques on peer-assisted CDNs is not enough. The basic idea of ARNI routing is to encapsulate messages in layers of encryption. For example, when a user sends a message to a destination, the user first fetch a set of nodes from a directory server and increase the message layer by layer, and then send the encrypted packet to the intermediate nodes. Each intermediate node peels off one layer of the encrypted packet until to the destination. However, we found there are several limitations of such naive solution. First, this solution can only preserve initiator anonymity. That means the responder doesn't know who is the initiator of the request. However, the initiator knows who the responder and who are the intermediate nodes in the circuit. And since the initiator has to communicate with the intermediate nodes to set up the circuit, there is non-negligible circuit setup latency. And also, by default, all the intermediate nodes are chosen globally at random, so the data transmission via the circuit can cause huge performance overhead. To address these limitations and achieve the three goals, we introduce various ideas in our system. First, we use peer server to directly construct the peer for each circuit for each request instead of peers. This way, both initiator and responder don't know each other. And also we introduce region-based circuit construction. The peer server directly chooses intermediate nodes in three regions near initiator, responder, and globally at random. We also use a new feature of HTML5 called WebRTC to make our contributions compatible with all the mainstream browsers like Chrome and Firefox. Now let's go through the workflow of our system. So in the initiation phase of our system, peers directly fetch resources from the content server and store the resources in the browser storage. After there are enough peers in the system, peers can directly fetch resources from the other peers. For example, when a peer sends a request to a peer server, the peer server instructs the initiator to send a request via an OR circuit to the responder, and the responder responds via the same circuit in a reverse manner to the initiator. Then the initiator reports the successful request to the peer server. Let's zoom into the details of region-based circuit construction. So when peers join the system, they upload their public key to a peer server. When a peer sends a resource request to a peer server, the peer server first selects a peer which has the requested resource as the responder, and then select a candidate set of peers near the initiator, and choose some of the nodes near in this region, and then select a candidate set of peers in near responder, and choose some intermediate nodes in this region. The remaining intermediate nodes are selected globally at random. Then the peer server encapsulates the request with layer encryption and sends back to the initiator. The initiator sends the encrypted packet to the intermediate nodes, and each intermediate node peel off one layer until to the responder. The responder gets the plaintext of the request and then prepare content with encryption of the symmetric key from the request, and then responds with this encrypted packet via the circuit in a reverse manner to the initiator. The initiator gets the plaintext of the content and then sends the successful request to the peer server. Now we know how our system works. So what's the anonymity guarantee of our system? We use the standard method called degree of anonymity to measure the uncertainty of identifying the initiator or responder in the anonymity site. After the observation of the adversary, the uncertainty of identifying a peer as initiator or responder decreases. The idea behind this method is to measure the degree of the remaining uncertainty. If you are interested in the analysis part, please take a look at our paper. Here I show you how to select parameters to achieve high level of anonymity. So basically, for the website operators, she can choose a large maximum number of intermediate nodes or a smaller fraction of intermediate nodes near the initiator or responder, or use a large total number of peers in the network. All these parameter selections can lead to a high level of anonymity. In conclusion of our analysis, when the maximum number of intermediate nodes is larger than 2, our system can preserve the standard degree of anonymity, which is achieved by previous work. We also evaluate our system. We consider a common scenario that CDN operators can place as servers in major cities. However, there are some users are not located in those cities. These users may have major latency to fetch resources from the edge servers. We deploy a site providing images of different size and place content server, peer server in one city, and 100 peers in another city. For the first experiment, we measure the network latency reduction. The baseline is the time that a user directly fetch resources from the content server. And we also measure the performance of Swarmify and our system in different settings. From this figure, we can clearly see that for a 4-node circuit, our system can provide around 50% of latency reduction, although it is lower than the performance of Swarmify and non-anonymous setting, but it's still much better than the baseline. In the second experiment, we measure the effect of distribution factors. In the figure, we can see that the leftmost bar and the rightmost bar represent the scenario that all intermediate nodes are selected near the initiator or responder. And the middle bar represents the scenario that all the intermediate nodes are chosen globally at random. The huge gap indicates that locating intermediate nodes near the initiator or responder can significantly reduce the network latency. Combining the anonymity analysis and the performance evaluation, we found there is a sweet spot, and that is with up to 2 intermediate nodes, our system can preserve adequate degree of anonymity and achieve desired performance. In conclusion, we introduce inference attacks on peer-assisted CDNs and develop anonymous peer-assisted CDN, aka APAC, to involve user to deliver content, at the same time preserve high degree of anonymity, achieve desired network latency, and also our system is compatible with current mainstream browsers. Thanks for your attention. That's all my talk, and the questions are welcome.